You'll recall from the very start of exponentials and logarithms that we talked about exponentials being growth and decay modelling functions. So they were able to model systems where we had an exponential growth of something or an exponential decay, so possibly the growth of a population within an ecosystem, or the decay of something, let's say an important thing, the decay of radioactive material in a real life scenario. Now, modelling these is vital that we are able to do, especially something like radioactive decay. And we have to be able to model these and find certain characteristics. And one key thing that it likes us to look for, and one key measure we have to be able to model, calculate and work with, is something called the half-life of a radioactive substance. So that's what we're going to look in this video. We're going to talk a bit about exponential growth and decay and about half-life of substances. Now, half-life is exactly as it sounds. No, I'm not referring to the computer game that came out a long time ago. What I'm talking about is the fact that it's the time taken for the mass of a radioactive substance to half, or to cut in half. Now, modelling these using exponential functions is a key thing we have to be able to do, and we have to be able to solve for these. So solve to find how long it takes for a half-life, how much is left, etc., things like that. And what we're going to do is we're going to look at a few examples of this and how we model these sorts of scenarios. So imagine I tell you the mass g grams of a radioactive sample after t years is given by this equation: g equals 100 e to the negative 3t. I want to know first what the initial mass of the sample was, and then I want to find the half-life of the sample. So these are typical types of question that you want. Now, initial mass of the sample means the mass at the start, and at the start the thing you should always assume is that t equals 0. No time is gone, you're starting it off, you're about to begin. That's when your initial sample is. So if you ever see that kind of phrase there, you're thinking right at the start of your situation, so t equals 0. And to get that, we substitute it into our equation. So we say that g equals 100 e to the negative 3 times 0. Now, negative 3 times 0 is 0. So it's 100 times e to the 0. And anything to the power of 0 is 1. So it's just 100. Now, this is a key thing you have to make sure you do in a situation like this as well. Put it back in context, especially with things like units. So our mass isn't 100. Our mass is 100 grams. So you have to make sure you put that back into place. So the initial mass of our substance is 100 grams. Now the second part is find the half-life of the radioactive substance. Now, half-life is the time at which g is half of what it initially started at. So if we know that initially g was 100, we know that the half-life is when g becomes 50 grams. So we know it's when it takes to get the mass down to 50 grams left of what we had at the start. So what we can then do is substitute that in here and find out what t is by solving that equation. So what we're able to say is that 50 equals 100 e to the negative 3t. And then it's a case of solving it. So if we divide both sides by 100, we have e to the negative 3t equals a half. Now we want to get rid of the e on this side. To get rid of it on here and we shift it across here, remember we have to take log to the base e of both sides. So what I end up getting is negative 3t equals log to the base e of a half. Once I've done that, I want to know ultimately what t is. Well, I know it's going to be negative a third log to the base e of a half. Now when I've got something like that, it's simply just a case of converting it into decimal, i.e. calculate it. And in this case, it's 0.231 to 3 decimal places. Excellent, we've got an answer, t equals that. But here's my question for you, what the hell does that mean? We don't know, because we now have to put it back into context. Now we know the half-life is 0.231, but 0.231 what? Well, look at the question. T is measured in years. So we then know that the time is equal to 0.231 years. But telling somebody that isn't exactly the most useful bit of information. What we really want to do is turn it into a unit of measure that's more relevant. So instead of 0.231 years, let's turn it into how many days. And to turn that into days, we do 0.231 times 365. If we do that, what we end up getting is 84.315 days. That's slightly better to tell somebody, oh, it took about 84 days for it to go through half of the sample, so to get to the half-life. Remember this sort of thing here, all right? We have to not only get an answer to the question, but make sure it's relevant and understandable. There's no point in doing something that doesn't make any sense. So let's look at another example of this, something that maybe looks at exponential growth. This one focused on decay. Let's look at that. Now the scenario is that the world's population in billions, t years after the year 1950, is given by this equation here. P equals 2.54 e to the power of 0.0178 t. First thing I want to know is what the world's population was in 1950, and then find to the nearest year the time taken for the population to double. So, what the world's population was like in 1950, well, think of the scenario. It's t years after 1950, so for that to be the case, 1950 is where we begin. So 1950 we know is our initial point, so we know that t equals 0. So we substitute that into our equation. So we know p equals 2.54 e to the 0.0178 times 0. Power is going to be 0, e to the power of 0 is 1. The population is 2.54, but 2.54 what? Well, look at the question. The world's population in billions. So it's not just 2.54 people, it's 2.54 billion people. We have to make sure we put it back in context. We cannot forget that. So the population to begin with is 2.54 billion people. Great, that's what happens in 1950. Find to the nearest year the time taken for the population to double. Well, what that means is that for our population to double, we want it to be 2 times what we initially had, so 2 times the 2.54. So 2 times the 2.54, that gives us a population of 5.08 billion, or just 5.08 for the scenario we're working with. What we then do is we substitute that in. We know that this is what we want to be equal to p. We're trying to solve it and find the t for that. So we know then that 5.08 equals 2.54 e to the 0.0178 t. And then it's a case of solving it. So divide both sides by 2.54. We then know that e to the 0.0178 t equals 5.08 divided by that. Well, that just equals 2. That's quite a nice convenient number. Excellent. We then take the log of both sides. We then know that 0.0178 t equals log to the base e of 2. And then from that, to get t on its own, we just divide both sides by the 0.0178. So we know t is equal to 1 divided by 0.0178, and that's multiplied by log to the base e of 2. So it's, again, this is the point where a calculator comes in handy. Plug it all in. What you end up getting is t equals 38.94. Great. 38.94 what though? We have to go to our context of the question again. So it's 38.94. Look back here. Years. So what we're then able to say is find to the nearest year the time taken for the population to double. We know it's going to be 38.94 years, but as I've just said, it's to the nearest year. So we round it up, we get 39 years. So 39 years after 1950, that's when the population will double. So 1989. These types of questions are very, very common to get in higher. We have to be able to work with exponential growth, exponential decay. We have to be able to understand what it means by initial values. So initial values when the time is equal to 0. When we start, we can't take this out of context and we can't think beyond this to start with. Then it's all about looking at what the question asks us. Are we doubling the population? Are we halving the population? Is it a quarter of the population? Think what it's asking and think how this relates to the scenario and how we can set up the equation just like we've done in both of these examples and then take it from there.